they can see what we did in class. So exponential functions can be used to model a variety of real-world situations. So we're going to learn to model situations involving exponential growth, like population growth or compound interest, and exponential decay, like depreciation and radioactive decay. So we're thinking big picture, and then we're going to spend a whole unit analyzing exponential functions. So here's a situation for you. If there's 6 bacteria in a culture and the number of bacteria triples each day, let's just fill in this table of values. So if it triples, that means you're multiplying the number by 3, right? So if you're multiplying the number by 3, fill in the rest of the table. Like 18, right? Should be the next number, right? Because 6 times 3 is 18. So if you could finish filling in the table. So get out your calculator. You're going to need it out anyway because. So we've got our multiplying by 3 each time. And why is this an exponential situation? Well, what if I just asked you what this number was and didn't do times 3, times 3, times 3, times 3? Couldn't I just do 6 times 3 and raise the 3 to the 1, 2, 3, 4, 5, the 5th power? 6 times 3 to the 5th, right, is 1458. So an exponent is just repeated multiplication, right? So whether I write 6 times 3 to the 5th or 6 times 3 times 3 times 3 times 3 times 3, I'll still get 1458. So exponents are just repeated multiplication. So let's review again how to use technology to view a scatter plot of the data. So you go to Stat, Edit, right? Stat, Edit, and then you should bring up your List 1 and List 2, clear out what's in there. If you need to clear it, you can arrow up so that you've highlighted List 1, and then just hit the Clear button and the Enter button. So arrow up, clear, Enter will clear out your list. So we're just going to view the day and the bacteria amount. So day 1 through 6 goes in list 1. 1, 2, 3, 4, 5, 6. And then the population of bacteria is what we're going to put in list 2. So 6, 1854, 62, 486, and 1458. Anyone need help getting the data in the calculator? Now's the time to ask. So on Tuesday, you could have your that little cheat sheet out of your notebook that says the steps on how to do a regression, but that's it. I want you to be able to enter it yourself using the technology after we've done it over 3 days. Did everyone get the data entered? So we want to view a scatter plot. So to view a scatter plot, the first thing is to go to Stat Plot up here above the Y equals menu and turn it on. So second Stat Plot, mine is currently off. If I hit Enter twice, it'll turn Plot 1 to on. And then it should be a scatter plot of List 1 and List 2. You can change your dots and you can change your color if you want to. But once your scatter plot is on, I just go to Zoom 9 because Zoom 9 is for stat view, and it should give you a scatter plot of your data on the screen. Does anyone need help getting to that point, or something didn't work? Because I am happy to check. Who needs some help on that? Okay, so now, once you've viewed the scatter plot, then you decide, is this linear, exponential, or quadratic? It's exponential. So to find the equation for the regression equation, it's under Stat, and you go over to Calculate. And you could do a linear regression, a quadratic regression, a cubic regression, depending on what type of function. If you go all the way down to choice 10, which is number 0, it'll let you do an exponential regression. So you can either just scroll down or hit the 0 key. It'll ask you, did you want to use list 1 and list 2? Yes. Where would you like to store your regression equation? I would like to store it in Y1 so I can see the graph on top of the data. So that's the part that you might want to add to the little cheat sheet you hit vars, y vars. So in this spot, you hit vars, y vars, function, y1. So if I type vars, y vars, function y1, when I hit calculate, it's going to store whatever my equation is in the y1 menu, and I can also write it down. But that way it's in there with all the decimal places, so it's a little bit of a shortcut, but you might want to write this down on the little cheat sheet that's in your notebook. So that is in your notebook right around where that 003 was, I think. This is the paper that I'm referring to. So stat calculate linear regression or change if necessary. List 1, list 2, and then I wrote calculate, push enter. So you might want to just add on that paper to store the regression equation, vars, y vars, function y1, just so you remember how to put it in there. And I should change this for next year so that I just print it for you, but I already printed it. So this is kind of the back door. If you forget to store the regression equation, here's how to get it to show up in your y equals menu. You go to y equals and either type in the regression equation or use this set of commands, vars, statistics, equation, regression equation. So there's another way down here to put it in the y equals menu. So now when I hit calculate, there's my regression equation. Y equals AB to the X power, where A is 2 and B is 3. So I'm going to record my regression equation. Y equals 2 times 3 raised to the X power. And I think you can see if I do just 2 times 3 to the first, I get 6, right? 2 times 3 squared, I get 18. 2 times 3 cubed, I get 54. So it says, what do you think the parts of the equation you found represent in the problem? Just obviously the 3 is the tripling, right? Because 2 times 3 is 6, 6 is not showing up in our equation right now, but usually this number represents our starting value, but 3 represents the tripling. So how many bacteria will be present day 10? So I can plug in 10 into my equation to figure out how many bacteria there will be on day 10. So 2 times 3 to the 10th. There's going to be 118,000 bacteria. 118,098. And I did 2 times 3 to the 10th power. So I want you to do a little bit of guess and check. How many days will it take for the bacteria to reach the carrying capacity of the dish, which is 1 million bacteria? So now they're consuming all of the nutrients, so they've reached the carrying capacity. So can you do some guess and check? Did you know that on the calculators, you could just arrow up to the previous equation, hit enter, and you'll get the equation back. And then you could change the number of days. You could also scroll through your table of values and just keep going down in the table. That's under second graph to get to the table, right? So by day 12, it's over 1 million, right? I just want to show you in the table of values. So this is the table on the calculator. See how it says this E6? Oh, sorry. Let's see. So it says E6 or E7. That's scientific notation. If you arrow over, see if I can make this darker. So if you arrow over to the Y value, it'll actually show you the Y value at the bottom of your screen, so you don't have to think about scientific notation. So see how like day 11 was 354,000. Day 12 is already over 1 million. So if you don't understand the E6, the scientific notation, if you put your calculator or your cursor there, it'll show you the amount at the bottom of your screen. So that's bacteria growth. So what about doubling pennies? So what if I told you I would give you 1 penny on day 1, then 2 pennies, then 4 pennies? How much pennies, or how many pennies would you have for 30 days? So we don't have to add up day 1, day 2, day 3, day 4. Just how much should I be paying you? How many pennies would I give you on the 30th day? So I don't think you want to multiply times 2, times 2, times 2, times 2, times 2, 30 times or 29 times. Think about a shortcut so that you don't have to do times 2, times 2, times 2, right? An exponential shortcut. Be whatever you're starting with, 1 penny, right? Times 2 raised to the 29th power. Do you all know where that exponent key is? It's the upside down caret button. That's the raising it to the 29th power. So you would have that many pennies. I'm just going to divide by 100 to put it into dollars. Let's see. I would have to give you 5 million, right? $368,709.12 just by the 30th day. That's an incredible amount of money. So if you can trick your parents into saying, well, I'll do this chore for you. You only have to give me a penny today, but you've got to double it every day for 30 days. I think they would go bankrupt because they'd have to pay you $5 million. So that'd be a pretty good trick. All right. Interest, compound interest. I don't know if you've seen compound interest before. We're definitely going to spend more time on interest when we study exponential functions, but I just wanted to expose you to compound interest, multiplying your money, and multiplying the interest over time. So a bank, they give you your interest every so often, whether it's monthly, annually, continuously, but your money is compounding over time. Same thing with the stock market. If there's a 7% increase each year on average for 7 years or 10 years, your money is compounding. That's how you want to grow your money. So I said, what if you invest $1,000 in a stock that earns 7% interest rate each year? How much would be in the account after 1 year? So I've given you 2 strategies. The first is to just multiply by 7%. You get your $70 of interest, and then you just add the interest to the original amount. Think of this as your old way, your less sophisticated algebra way. Here's what we want to start doing this year is using exponents to multiply for us faster. So how can I get my 7% multiplied by 1.07? That gives you back your initial amount of 1,000 plus your additional interest of 7%. So if you want to get to year 2, 3, 5, 10, and 20, all you have to do is use the function that you're starting with $1,000 and you're multiplying by 1.07 to however many years, right? Because that gives you your original amount back plus your interest after the first year, after the second year, after the third, fourth, fifth year. So the exponent is taking some of that calculating work away from us. So try to fill out the rest of the table. So I just want to show you, I didn't guess and check. I used the function. You don't have to know this function right now, but it's your starting value times your ratio, like of a half. How many times do I have to multiply 20 by a half? So I put an X up there. So when I go to my table, I can kind of quickly, it's hard to see, but it goes, 20, 10, 5, 2.5, 1.5, 0.625, 0.3125 after just 1, 2, 3, 4, 5, 6, about 7 cycles. Yeah, so like 3.5 to 4 minutes. 3.5 to 4 minutes. But you really never get, right? Really never get to 0. Right? Because it's always halving your distance. So one trait of an exponential graph that you will learn is it has an asymptote. It never actually gets to 0. It could get to 0.000000001, but it never actually touches the x-axis. It doesn't get to 0 because you can always cut it in half a little bit more. What about March Madness, which we missed having this year, but any type of single elimination tournament, the top teams all play, right? So you've got 64 teams in round 1, but every single game played has a loser. So how many teams are still in after the first round? 32. Right? And then they go down to the Sweet 16, right? And then the Elite 8, and then the Final 4. And then round 6 is actually producing the winner, right? Because of the two teams, there will be a winner. So you don't have to go one more column till you get to 1, because the game that has 2 people, there will be a winner from that game, right? So there'd be 6 total rounds, right? Round 1, 2, 3, 4, 5, 6th round is the finals. So what about the Australian Open? If there's 128 tennis players, how many rounds would they need in their tournament? Just one more round, right? Because it would just start at 128. So you can see the patterns generated by multiplying by 2 or multiplying by 3 or multiplying by a half are all exponential situations. All right, so this last page, before we take a break, I think we're going to do radioactive dice when we come back in. So let's do situation 6 and then take a pause. This is, sure. So bouncing a ball is exponential. So it says most athletes consider a true bounce important in the world of sports. Baseball players can be dismayed when a baseball takes a bad hop. Basketball officials commonly drop a game ball from chest height to see the return height. If the ball bounces well above the waist, it's too bouncy. If it bounces below the waist, it's too flat. So they might have to adjust the inflation of the ball. Remember Patriots with their do they have overinflated footballs? Was that the scandal? Deflated. Oh, it was deflated. And then what happens? You can catch it easier if there's less air in it. So anyway, so there is a fairness in the ball being consistent. A tennis or ping pong player must react instantly to the bounce of the ball. So these athletes can't afford to play games with unpredictable bounces. So I just gave you 2 different sets of data. So here's a tennis ball, and I did some calculations and came up with some heights of bounces. Here's a basketball. I dropped them from different heights, but within their own consistent table, you should be able to calculate the rebound ratio. So the rebound ratio is found by dividing the bounce height by the original height. So I could just take 44 and divide by 80. Let's see, 44 divided by 80 is 0.55. So that was the rebound ratio, but this is data. So it'd be good to check all of our rebound ratios. So take 24 and divide by 44 and see if you get the same ratio. So 24 divided by 44, it is about 0.55 again, right? So it should be consistent. If I take 13, here I am. If I take 13 and divide by 24, 0.54 that time, 8 divided by 13. So each bounce, oh, that one was off, 0.6 at the end. So about 0.55 or 0.6, I would say, would be the rebound ratio, right? So I took 44 and divided by 80, right? How high did it go on the bounce? The rebound ratio is going to be less than 1, right? Gravity is pulling it down, so it's not going to bounce higher than where you dropped it from, right? Nothing is propelling it to go higher. So what would you say the rebound ratio for the basketball is? Yeah, 0.72. If I just compare the first 2, let's see, 31 divided by 43. Yeah, 0.72 again. 22 divided by 31, 0.71. Yeah, so right around 0.7 or 0.72 is fine. So even though, I dropped this from less of a height, so you just couldn't compare which one was bouncier, the basketball had a higher rebound ratio than the tennis ball. How would you estimate the return height of each ball after the 5th bounce? So the 5th bounce, you really only have to go one more bounce in the table, right? So the 5th bounce, you're going to use your rebound ratio and see what the next predicted height was. So you're going to multiply 8 times 0.55, and you're going to multiply 16 times 0.72 to predict the next bounce. So it tells you how much of the original height you would get. So I got, is this 4.4 inches? And then this one would be 11.5 inches. Everyone see how I got that? I took my fourth bounce and multiplied by the ratio. And then my last question on this page before we pause for a little bit of break, and then we'll do the back when we come back. What other types of balls would have large rebound ratios or smaller rebound ratios? So some of the, different balls you use in sports. What do you think would have a bouncier or less bouncy? Yeah. What? Yep. So tennis ball we had in this problem. Can you think of something other than a tennis ball or basketball? Yeah. Yeah, bouncy ball, I would say would be a high rebound ratio, right? A bouncy ball, maybe. The golf ball is the one that we used for our day one kind of collecting data. What about a lower rebound ratio? Yeah. Yeah, I'd say baseball is probably less. Bowling ball would probably just go thud, right? Yeah, so you get the idea. Right, so a rebound ratio is something between like 0 and 1. So 0.2 would be a pretty low rebound ratio. 0.7 was a pretty high rebound ratio. I forget with our golf ball. I think we got around 0.6 that day when we were trying it, if you remember. So, all right, so I'm going to pause.